subspace, we should determine the dimension of the following bases, right? Then they give us this. The first one, they give us this. First thing that you need to check is how many variables are you given. That will be your set, right? Then secondly, you need to check how many or what space is this. We have 1, 2, 3, 4. All right. So if we come here, we're going to first show that W is a subspace of R4 because we're in the space of 4. So you see what I said? You check how many, the space is 1, 2, 3, 4 if the question is like this. Right. Then if it's in this case, we're going to check how many columns we have. How many columns do we have? 1, 2. Then we'll know the space we're in. Then this one, they say W is a line through the origin. What is the equation of the one through the origin? Can be y is equals to mx, because we don't know what the gradient is. We can just keep it as y equals to mx. So let's look at the examples on how do we compute this. But the main aim here is to separate this into 2, because we have 2 unknown variables. You see, right? So we're going to separate it into 2. So it means that when we come and check, we are given that W is equal to this. So we can separate this into 2. The first one being A. If we check, the first number has 3A. The second one doesn't have A, so we're going to leave this as 0. The third one has 4A. We put 4A here. The fourth one doesn't have A. We leave this as 0. And then on the last one, it will be represented for B. We say the first one does not have a B. We put 0. Second one has B. We put B. The fourth one has minus B. We put minus B. The third one has minus B, and then the fourth one has minus 3B. We put minus 3B here. Then we factor out our variables. Then whatever we get there will be our basis. You see right now? If we check it, they say from this, we can see that the basis of W is 3040, and it's minus, it's 0, 1, minus 1, minus 3. With 2 elements, right? Or we have 2 vectors in here. It means that the dimension, remember, the dimension of W is the number of vectors found in the basis. Right, let's check the definition. I think they might have given us the definition of a dimension. They say that if V is a vector space, has a basis consisting of n vectors, then the number of n is the dimension of V, which is denoted by dim V equals to n. So those numbers of bases there will be our dimension. If we check it, we found 2 vectors. It means that the dimension of this set is equal to 2. All right. Then the dimension of this will be equal to 2. Now we check B. B says that we can easily show that W. How many variables do we have here? Oh, it's 3, right? Yeah, we should have 3 space. Yeah, we have 3 variables. We should not 3 space. We should have 3 vectors, since we have 3 variables. So this one's, yeah, it's 3 vectors. I thought I saw AB. So we can show that W is a subspace of 3, 2. How do we know that it's 3 true? It's 3 rows, 2 columns. You see, right? Now, since it's 3 rows, 2 columns, now already we know the space we're in, right? We're in the space of 3, 2. So now we say that we have 3 variables, so we must separate this into 3. Since we have 3 unknown variables, you see, right? You must separate this into 3. You can just say plus, 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 and you leave this in a 3 by 2 format. Then the first one has A, doesn't have A, it's 0, doesn't have A, it's 0. Then we check, is there B? There's a minus B. There's no B here, so it will be 0. We have minus B, we have no 0. Then here we have no B, also it's a 0. Then we check here, we do not have a 0. We do not have, or we have an A here for this one. But let me do it like this so that we can understand how do we check, right? Let me do this, because I think I might lose you if I'm doing it this way. So let me say this. You are going to check here. I think the first one represents an A. you're going to check here if there's an A. You check here if there's an A. Here you only check A. So let's check on the first row, the first column. We have 2A here, which is coming from here. Here there's no A, there's no A, so these ones will remain as 0. Is right? We come to the second row. We come to the second column, not row. We come to the second column. First one doesn't have A, so it's 0. Second one has an A, it's A. Doesn't have A, it's 0. Is right? The same way we do it the same way. We check for the second set. We say for the second vector, we're saying that now we are checking a B here. We check a B here. The first one has minus B, we put minus B. This does not have a B, does not have a B, so it's 0, 0. We check a B here, it's only down here, so this is a B, the rest is 0, 0. We come here also, we check for a C, each. You see, right? Now, when we are busy checking for a C, we see that we're checking for a C. We see that C is found here on the first column. So we'll put a minus C there. Here it's all zeros. Here C is found on the first one and second one. So here we have 3C, we have minus 4C. Here we have a 0. Right? From there now we can now factor out our variables. When I factor out my variables, I find that our vectors, our bases are these. These are our bases. You see, right? We have 3 bases. Then I put it, I said, therefore, B will be equal to the set of this, which forms a basis for W. And hence the dimension will be the number of elements within the basis, which is 3. Or the number of vectors. You see, right? Now, when you come to the last one, they say that we should represent the line through the origin. And I said that we can represent it something like this. You can change A to M if you want. Or use A, you can use variable any constant here for a gradient. Then, it means that W will be equal to, since in an origin form we only have XY. So it means that this will be X, this will be our Y. And we know that Y is equal to AX, so we can just substitute X. So we're making this in terms of X, if it's possible, so that we can factor out. You see, right? Or someone could make it in terms of Y. It's up to you how you do it. If you put it in terms of X, then you factor out an X, this is what you're going to get. So the form of the basis is this one. You see, right? Or someone could decide and say, since Y is equal to AX, if I make X up with the formula, I'm going to get Y over A. So this here would come and be like W is equal to, our X is Y over A. Then our Y here. Then if we take out Y, so let me say this. So be 1 over A, this will be 1. Right? But we prefer this one because they spoke about a line through the origin, and we know that it's always Y that is the subject of the formula. So that one would be more preferred, this one. So most cases of a basis of where you have to make something subject to the formula, you can have multiple solutions, but then it should be correct, right? Now here we have one dimension because we have one vector within this set. So here's another thing. Here are some properties that we can be asked in the multiple choice. They say we should let W be a subspace of a finite dimensional vector space V. Then they say W is a finite dimensional and the dimension of W is always less or equal to dimension of V. If W is a subspace, in other words, if W, it's like this. If W is a subspace of V, then this means that the dimension of W will always be less or equal to the dimension of V. According to that, they just come and put dim both sides. You see right now? So that is what it is saying. And the dimension of these two will only be equal if V and W are equal. This is 1 to 1. You see, right? So the dimension of this will always be equal. So if you want to show that a vector space is 1 to 1, it means that you would show that, you would assume that it has a subspace, and you show that the dimension of the you assume that the dimension of that subspace is equal to the dimension of the vector space. Then you show that they are both equal. We say, right? So now in this case, We can confirm this theorem from the above example 5.11. Which one? Yes, this one. If we check, we're in a space of R4. The dimension of R4 will always be that 4 there. You see, right? But this year we found that the basis is 2. If we find the basis is 2, it means that from here 2 should always be less or equals to 4. So here in this case 2 is less than 4. So we have confirmed that theorem. Also on the second one, we're in a space of 3 by 2. You remember yesterday I showed you that this one, you can find the dimension of it by saying we are multiplying those numbers there. You say, right, you get the 6. So the dimension of this is 6, but the dimension of W in that case it was 3. We have 3 unknown variables, so we got 3 vectors. You say, right? The same thing as the dimension of R2. Dimension of R2 will be 2, but the dimension of W in that one, which passes through the origin, we found that we have 1 vector, right? Which was 1 in A. So we get that. Now let's look at this tutorial. I think we've already done these 3, and I told you to go and finish this one because it was too long. So let's look at this one. We're going to look at D. D, we are given that we have 1 plus x and we have 2x minus x squared in P2. Okay, it's here. So I told you to go finish that. So let me erase this. Let me try to wipe this screen. I don't know why it seems like it's oily or something. Oh, this pen is starting to overreact. Let me not try. Let me see. So for you to finish this, you must change this matrix to a reduced Raytron form. Then that's when you can finish, right? And then now we are given D. On D, we are given this. We are given that. Let me see. We are given that S. They say S is equal to 1 plus x, 2x minus x squared. One plus x, x minus x squared. Yeah, I don't think the problem is. Let me just change the tip of the pen. Then maybe the problem might be the tip. Yeah, I think the problem was the tip of the pen. So yeah, they say that this is in P, right? This is in P2. So for us to solve this, right, first remember we must check if this is a basis. So we're going to write this in a linear combination. We're going to say first, before I write that in a linear combination, let me just let ax squared plus bx plus, see, because this is in the degree at most 2, so here it must be, the highest should be 2, which is an element of P2, such that we can express this as a linear combination of this. Right, and here we get what? We get alpha plus 2 beta x. Let me just write it like this, it's fine. It's alpha plus alpha x. Let me write it step by step once. Actually, I can even remove this here. Actually, you don't have to put this because there are no commas, right? You can just say alpha plus alpha x plus 2 beta x minus beta x squared, which I can now rearrange them according to the x squared, right? We have minus beta x squared plus I have beta, I have alpha plus 2 beta x plus alpha. And then here it will be ax squared plus bx plus c. Then I equate this. I equate a to be equal to minus beta. I equate b to be equal to alpha plus 2 beta. Then I equate c to be equal to alpha. You see, right? And then if we check here, we have this. So we can try anything to solve this. Let's check if I put it like this. If I say beta is equal to minus, let's say I was going to use simultaneous, right? But in this case of these ones, it's not wise to use simultaneous. And then I would have, or before I even use simultaneous, let's just check the determinant. Let's put this in this case in matrices form. For the first one, do we have alpha? Alpha was the first one. No, we don't have alpha, so it's 0. And then minus 1. And then we have this one is alpha, b is alpha, and then we have 2 beta. We have 1 alpha, 0 beta. So now we have this, right? And we have 2 scalars, which is alpha and beta, which this will be equal to a, b, c. Now we can't check the determinant of this because it's not a square matrix. So it means that we must check the other things, right? So we must check if we have this. Let me not give them any name. Minus 1, 1. We must check the system. We have A, B, C. It says that we must have a leading one here. So I'm going to interchange these two. I'm taking the closest leading one. So I'm going to have 1, 2, B, 0 minus 1, A, 1, 0, C. Then I must change the last one to a 0 now. This will be, it will be 1, 2, 0, minus 1, BA. Changing this one to a 0 is row 3 minus row 1. Y minus 1 is 0. This is minus 2. C minus B. Then this one now should be a leading one, right? We change that to a leading one. It's 1, 2, 0, 1. B, this will be minus A, 0 minus 2, C minus B, minus row 2. So we have this, right? Already this is what we found from the beginning, that A is equal to minus beta, and also beta is equal to minus A. You see, right? And also we found that alpha plus 2 beta is equal to B. You see, right? So since already we have these, also for conjure, which engines with the extra space, they are there on the guide. Those 10 engines. Unless if you, I don't know, what is your question based on? So we have these, right? But check, we're in P2. The space of P2 should be you see the space of P2 is 3, right? Because we have P0, P1, P3, P2 man, P2. Even though this is not the case to check whether, it's not the easiest way to check whether this will give us a 0 or not, right? But this is what we have. Or we can try to disprove it by checking from here. If we let A, B equals to B, B equals to C to be 0, for us to check if this is linearly independent or not, because here if we just conclude and say that this is a spanning set, we might not be sure, because for it to span, since we're in P2, in most cases we should be having 3 leading ones, because we have it's a space of 3, you see, right? Because we include 0, so 0, 1, 2. So if we let those two be equals to 0, it means that we're having 1, 2, 0, 1, 0 to check if this is linearly independent. So this will be 0, 0, 0. And then we're going to have that this is alpha, this is beta. So we can even change this to a 0, because we want to change this to a reduced rotation form. This will be 0, 1, 0, 0 minus 2, 0. So this would be row 1 minus, this would be 2, row 2. So this will be 1, this will be 0, 0. Now, if we check alpha, we have alpha, we have beta. Alpha will be equals to 0, beta will be equals to 0. You see, right? But the spanning set, this one does not span, because we're in P2. Remember I said that P2 is we're in a space of 3 leading ones. So we should be having 3 leading ones for this to span. You see, right? So this one can be tricky. That's why I decided to say, I wanted to skip it, but some they can get here. You get that this is linearly independent. Then you come here, you get that you're having 2 leading ones. Then this thing will give you false hopes to say that this thing is a spanning set. But in this case, it does not span, because we should be having 3 leading ones. You see, right? So we see that this does not span. It means that we can see now that S, let me write, S is linearly independent, but does not span is it M32? No, it's P2. Span P2. You said right. It's S is linearly independent, but then it does not span P2. So now we see that for this to span, we should have 3 leading ones, since we're in P2. If you're in P2, you should have 3 leading ones. If you're in P3, you should have 4 leading ones. If you're in P0, you should have 1 leading one. If you're in P1, you should have 2 leading ones. So you always add 1. This is like, it should be n plus 1. I can see that this is Pn, right? Then the dimension should be n plus 1. Let me go back to that property. You'll see that property. Let's go and check that property. There's a property somewhere that says that. Let me come here. We'll see that property. There's a property that says something like this. Yeah, here's it. You see, right? So the dimension of Pn should be equal to n plus 1. So this is also the case when we are here checking if it spans or not. If we're in P2, we should get 3 leading ones. You see, right? So now we got 2 leading ones there. It means that it does not span. So this won't span. Any question? If you have any question, guys, you can ask. So I believe that since we have done that, I believe that we know how to find the basis of this, and this one. I just want you to go and check them. Please write them. Then you can write these ones, right? You try to check if you did understand what I was telling you. If you can be able to find these, guys, you are ready for the test, right? So if you can be able to find those, then you also determine their dimension. And then here they say find the basis for the following subspace. Here the question was saying what the phrase is determine whether the set B is a basis for vector space V. also determine the basis here and check if this thing is a basis. First check if it's a basis, and then you determine the dimension. Then here, I think I've sent solutions for these three. You can check them, then you try these two, right? You also give us the dimensions, determine the dimensions. Then let me see if we have any other tutorial. They say determine the dimension of the following vector space. Here we're given that P of X is an element of P2 such that P1 is equal to 0. Then they say determine the dimension of this. So you can try to check the dimension of this. Then they say find the formula for the dimension of vector space of symmetric n by n matrices. The formula for this one, obviously we've seen it there, should be n, the dimension of, let's say the matrices is n. This would be equal to n times n. You say right. Then you'll check that. And also I think you can just check what are the dimensions here, then I'll correct you when we meet. Right, then let me see if there's any other that I can look at. Yeah, so we have I don't know, did they teach you guys the coordinates in class? Did they teach you guys the coordinates? But the coordinates are simple. I'm sure we can see what are the coordinates here. Did they teach you the coordinates?
Yes.
They did, right? But we can see, we know, I've told you before that the coordinates are just these constants, right? The coordinates are just these constants. There's nothing new. They just had to come and give it a new name. These are the coordinates of the basis. You see, right? There's nothing new here. They just came and gave it a name. So here, let's see what they're saying about the coordinates. They're saying definition 6.1 coordinates. They say let B equals to a set or collection of vectors. Be a basis for a vector space V. And we let V be a vector space in V. And write V is equal to the linear combination of these vectors together with their coordinates. Then they say that C1, C2 up until they were supposed to say Cn here. Up until Cn are called the coordinates of V with respect to B. You see, right? Then they say we should determine the column vector. Now, they say this is called the coordinate of vectors, or vector of V with respect to B. So this is V with respect to that B. Always the small one will always be called with respect to. You say, right? Okay, let me see. I think I should have answered this question here. What is the dimension of this one, of V here? Who can tell me what is the dimension of this? It's what? It's 3. Okay, let's write this. Let's check. They say P1 is equal to C, right? And we know if Px is equal to Px is an element of P2, it means that we can write Px as equal to what? Ax squared plus Bx plus C, right? Do you agree? Do you agree? We can write this in this case. Now, after writing this in this case, let me show you this. P0 is equal to C in this case. P1 will be equal to Bx. You see, right now? And then P2, this will be equal to this, such that x is equal to 1 in this one, which is fine. Then this one, I think we can make it what? Yeah, we can leave it like this because we don't have x. This one we don't have x. Then this one would be P2, which in this case we're going to have, it would be C, such that this one would be, let me say, our x would be 2, and this one is Px, right? But we can also express it like this. Let me just express it in this way. This one can be expressed. Let's say P1. I just come and plug. We say that P1 is equal to 0, so this will be the simplest way to to use it. Unless if we're in a proof, we'd use the other one. Yeah, this will be the simplest way. P1, they say that it's 0, so this will be 0. This is A plus B plus C. Do you agree? Then from here, can't we express one vector as a linear combination of the other ones? We can, right? Do you agree with me that we can express one vector as the linear combination of the other ones? Do you agree, guys? Guys, do you agree that I can express one thing as a linear combination of the others here? I can even say C is equals to minus A minus B. Do you agree? Meaning that if I have A, B, C, this would be equals to A, B, minus A minus B. Which in this one, how many unknown variables do we have here?
2.
2, right? It means that this will be broken down to, if this is with respect to A, it will be A 0 minus A plus, this will be 0 B minus B. Then how many vectors were we able to structure out from this? How many vectors were we able to structure out?
2.
2. So it means that the dimension will be 2. You see, right? So we can solve this in this way. We check that the dimension is equals to 2. So let's see what else can we have. So let me do this. So this one will be in this case, right? Yeah, it's fine. So just have to erase it. So the dimension of this one would be 2. So you just do it that way. I think that way it's simple to say it's 2 because of this, right? They told us this, but if this was just a normal set, it's because of this such that this gave us a point to say that we can express one vector as a linear combination of the other vectors. We say, right? But if this was some number other than a 0, it would be a different story. You say, right? Then they say we must find out, but I've already showed you the formula for this one. Now, let's see. This one, they say V is equals to they say V is equals to Px element of P2, right? And then they say such that X times P prime X is equals to Px. So how can we express this? Let's express it in this way. First, we can let, since P of X is an element of P2, meaning that we can let Px to be equals to Ax squared plus Bx plus C. And P prime X, we derive this once. We have 2Ax plus B. Do you agree? So we'll have this. Now, the equation is saying this. It's saying that X times this 2Ax plus B will be equals to Ax squared plus Bx plus C, which is this one, right? Then this side we're going to have 2A x squared plus Bx. This will be equals to Ax squared plus Bx plus C. When I take this to the other side, this Ax, I'm going to have Ax squared. When I take the Bx to the other side, it will cancel out. When I take the C to the other side, I'll have A squared is equals to minus C, which is equals to 0. You see, right? And if we check this side, it's like we're having this Ax squared plus 0x plus 0. So I can equate A to this. So meaning that A, this one would mean that A is equals to 0 and C is equals to 0. But then this one, B is unknown. You see, right? So it means that I can try to write this in this way. I'll say that this dimension, I'm going to have this. I'm going to have A, B, C. What is our A? A is 0. B we don't know, so we just write B because B is unknown, right? Then here we have C, which is 0. Now we're able to only find one vector. You see, right? Then the dimension of this will be equals to 1. D, you can check it, guys. I've done similar thing. It will waste a lot of time because having to write them takes a lot of time. So you can try this, then you ask me if you're correct or not. But do we understand the one which I just wrote now? Is it clear? So these are what you're going to be doing if you're given a condition. I wanted to leave this as an exercise, but I realized that that might be a bit difficult. So when you go back to the coordinates, they say we should determine the vector that has the coordinates. This, in other words, we should write this in a linear combination together with their scalar. So it means that -3 will come to the first vector, 2 will come to the second vector, 1 will come to the last vector, and then we add them and find the vector that they say we must find. You see, right? Just a simple procedure. So we're going to say this. We're going to say, and the vector here they give it to us is px. So we're going to say px, which is what they wrote down. I think they wrote it somewhere here. Px is equal to -3 times the first vector, 2 times the second one, 1 times this one. Then we simplify them and we get this vector. And then this is the vector that has the coordinates -3, 2, 1. Now here they say we must find the vector v, which has these coordinates with respect to this. So the first one will get a 2, this one will get a -1, which is this. You see that this one is simple, right? Asking questions based like this, they are the simplest. Any question here, we all fine. Are we all fine? Yeah, for this one, let me check. For this one, you can try to find, right, the dimension, but according to, if I try to inspect here, let me try to inspect. If I take this minus this, 1 minus 0, I'm going to get a 1. 0 minus 1, I'm going to get a -1. 0 minus 1, I'm going to get -1. Then 1 minus 0, I'm going to get a 1. So already I know that this 2 can generate this vector. And also this 2 can generate this one. So it means that these two, these two are our dimension. They will count on our dimension. So we can have our dimension as being 2. They'll bring you something like this in a multiple choice. You must be able to inspect. So the dimension of this one can be 2 of D. You can try to do it and see if you'll succeed, right? But in this case, that's how we'll be doing it. So you can try to do it in a computation way and see if you'll get the answer. So we come to this one, example 6.3. They say finding coordinates of vectors relative to standard basis. They say find the coordinate of vector, which is equal to, this is a 3D. This way an R3 actually. Let me say R3, because even if they had not told us this is the space of 3, 1, 2, 3, relative to the standard basis. When they say they want the standard basis, our standard basis will be this. Let me just say A will be equal to A1, A2, A3. Okay, let me write it like this. This is our standard basis. I think we have seen standard basis from the beginning to A3. Our E1, since we're in 3D, we're going to have 3 spaces. The first one will have a 1 from the beginning. The second one will have a 1 here. The third one will have a 1 at the end. So they give us a vector. They say we must find the coordinates. So we're going to represent this in a linear combination of these with scalars. So since these are just standard bases, the standard bases will always have these as scalars, 2, 5, 9. You see, right? But if you're not sure, you can just equate them to unknown variables, then or unknown scalars, and then you start finding those scalars, and then those will be your coordinates. You see, right? So you need to know the standard basis. Now we come to this one. They say a vector A is equal to, with respect to the standard basis of M22. Now the standard basis of M22 here, B will be equal to, the first one, the 1 will come here. The second one, the 1 will come here. So since this is 2 by 2, we're going to have 4 standard bases. The third one will come here. The fourth one will be on the last part. Already again, we know the dimension of empty2. The dimension of empty2 is 2 by 2, which is 4. So we must have 4 vectors within the standard bases. You say right. It means that if this was 2 by 3, we must have 6 standard bases within. Let's check what they did. So we have 4 of them, as you can see. And they should be in order. The first one should always be here, second one here, third one here, the fourth one here. They go like this: 1, 2, 3, 4, 5, 6. You move like that. You say right while you're counting. Now we come and say that if we have this, let's say I had since these are standard bases, the constants will always remain as they are, right? This one should have been 5 here. Yeah, -4, 3, -1. You say right. These are just going to come like if it's the standard basis. But if it's not the standard basis, it means that here you would put some scalars. Here, you would put alpha, beta, gamma, and you put W, something like that. It's just say plus. If this was not the standard basis, you say right. But since the standard basis, you're just gonna take those coordinates here, those values from the vector, and put them here. Now this will be the vector that we get after adding everything. So let's see. The coordinates of the vector will remain that. So they'll be in that case. So this is how you're going to write your coordinates, right? In this case, you see they're written like this. What by 1. What by 1. How many there are? If there are 4, it's 4 by 1. If there are 3, it's 3 by 1. You're always going to put them like that, your coordinates. So that's another thing which you should know. And then, let's see what else we can look at. They say finding the coordinates of vector relative to non-standard bases. These ones are not standard bases. They say this is relative. We are going to write this in a linear combination of scalars. You can put x, y, z. Then you equate to this. You say, right, let's check. We're going to do that. Or you say A, B, C. They choose A, B, C. Now you start solving for these scalars. After getting, let's see what they got for their scalars. Obviously, I won't show you how to solve scalars. I've been showing you that. You're going to try to find this is the solution system for this. If it's linearly independent or not. And then you found it, right? Not linearly independent. And if you check that it is unique or not. When you find this, you found that A is equals to 1, so you're gonna put your vectors like if this was V with respect to the non-standard basis, right? You found 1, -1, and 2, so it means that this would be your coordinate. You say right. That's I say that you guys have done these things. You just didn't know that these are called coordinates. You were just being told all along that these are These are coefficients. You say right, or scalars. Now we check the second question. The second question says that we should find the basis of px, which is equal to this degree at most 2, right? And the basis is this. You're also going to represent this basis as a linear combination of those scalars. Then now you equate it to that this vector or this equation. Then you start simplifying. Then you solve for those scalars. After finding the scalars, you put them in the form of, if they are 3, it's 3 by 1. You say right, pxb must always write like this. So as I said, this is simple, guys. If you have done this, as I said, so when we meet, we're going to start with tutorial 6. When we meet, we're going to start with tutorial 6. We'll see with that. We'll start with tutorial 6. So it seems like I'm gonna be at maths building around 12. I thought I would be done by 11, but then you see that we're still in a class, so I need to prepare. So when we meet contact, we're gonna do from tutorial 6. I'm not gonna do everything, I'm just gonna take few. So for now, you can try to attempt them, right? So that when we meet, you already tell me which one to attempt, which one to. If you don't know which one I should attempt, then I'll attempt them myself. So today we're gonna attempt anything in the tutorial, right? So our main aim should be the tutorial. So tell me which one do you want me to look at the tutorial so that we can plan our time effectively. Remember, we only have 3 hours or less, so we don't have the entire day, and there are a lot of tutorials we can't be able to finish.